the error will be right here and also right here at their maximum, right? So this is the problem caused by this towing approximation. So yeah, the next one will be a video to show you that how we can use this off-axis frustum to build some very interesting demo. Okay, so let me play this video for you, and you can have a look. Okay, so it gives you the illusion that the two characters are standing above the screen, right? Yeah, so this is another one. Okay. This is another one. It feels like 3D, right? Especially when you move, okay. So yeah, so this is exactly the same as we discussed in the cave, okay? So you can imagine there is a camera and you just use the camera to connect the dots, okay, the four corners of the screen to the camera, and you have the off-axis frustum, right? The only problem would be how you can write this in Unity, right? This is actually very straightforward. You just manipulate the projection matrix, okay? So there is actually, I would say, not very simple set of formulas for you to do so, okay? But I will not cover that because it takes quite a long time to explain and also do all the calculations. Yeah, but this calculation is very easy for computers to do, okay? Okay, so the next one would be the Cornell box. Okay, so this is a very important concept. This concept basically tells you what we wish to achieve ultimately for visual rendering. Okay, so this is a test. A Cornell box is a test. Okay, so this test aims to determine the accuracy of the rendering software by comparing the rendered scene with an actual photograph of the same scene. Okay, so for example, why it is called Cornell box? Okay, because this concept was proposed by Cornell University Computer Graphics Group. Okay, so yeah, so for example, these two, one of them is actually an actual photograph. Okay, the other one is a computer rendered. Okay, so anyone can tell me which one is actually a photograph? The left one or the right one? The left one or the right one? Okay. The right one is rendered or real? The real one, okay, you said the right one, okay. So anyone think the left one is the real one, the real photograph? Okay, so this question actually for me is very difficult, but I found a very tiny difference in these two photos. So I can always tell when I teach this subject, okay? It's not some markers I put on the PowerPoint slide, okay? I didn't do that. This is in the original photo, okay? So if you look at this part, and also this part, okay, you will find that this is an actual photograph. Okay, this is an actual photograph. Okay, this is some wood planks they used to build this box. Okay, okay, so yeah, and also another place that can give you some hint that one picture is not computer rendered. It's around this area. Okay, I don't know whether you can see it very clearly. Okay, I don't know whether you can see it very clearly on your screen and also on this screen. Okay, but on this screen it's very clear. Okay, so this is a very organic shape. Okay, it has an more like an uneven kind of, change to the lighting condition. Okay, so for this part, you can tell why it is like so. Okay, I don't know. I haven't investigated this. Okay, why it's created like this. Okay, but basically defects makes the real world. Okay, this might be a defect. Okay, I don't know what is it because of some of the surfaces of this box is not very even. I don't know. Okay, it can also created by the light bulb. I don't know. Okay, but you can imagine this kind of defect will only occur in a real world photo, right? Yeah, so this is the Cornell box. But in general, I think these two renderings are very close to each other. Sorry, the actual rendering is very close to the real photo, right? So yeah, so in this particular part of the lecture, I will just quickly go through some lighting, some different types of lights, and also light map and the light probes, because I have already covered them in the tutorial. Then we will dive into the details of real-time ray tracing, okay, real-time ray tracing, and also path tracing. Okay, so for lighting, as you can imagine that if the scene has no light, then basically we have a pitch black scene, right? So we must have some light, okay? So by default, even you go to Unity, you create a new scene, you delete the directional light, okay? So the directional light is the default light you will have when you create an empty scene, okay? Even you delete that, you put a box inside, that you can still see the box. It's not pitch black, okay? That is simply because we always have the ambient light in the scene, okay? If you want to make it pitch black, you have to turn down the ambient light, make it dark black, okay, very, very dark, and then you have to delete the skybox, okay, so that the skybox does not give you any ambient light, okay? So the ambient light can come from the skybox as well as a preset color, okay? You can set a color in Unity, okay? So the next one would be directional light, very straightforward, right? I guess you all know that. Point light, okay, so just like any light bulbs, okay. Spotlight, which is also very, common. So for example, the projector is a spotlight, right? So area light, okay, so all the panels, light panels, and also an ordinary, for example, a screen, okay, all the reflection of these projection walls, right? So they are all area lights. So yeah, I will not go through this one by one. Just remember that ambient light is always there. It does not cast any shadows. And you can imagine it's a very even light to all the objects within your scene, okay? Directional light can cast shadows, but it can only do some very rough calculations for the computer to do it in real time, okay? So that's why sometimes you see the shadows are not very good, and sometimes, it is a fast and useful way to do some very interesting shadows, okay? Yeah, this is directional light. So point light is located in as a point in space, okay? It's just like a light bulb, okay? You can also do some, you always use this light, point lights to do some local lighting, okay? Remember, do not put a lot of point lights in your scene, especially if your scene are not baked in advance, okay? It will dramatically make the scene very hard to render. Yeah, so this is a point light. We also have the spotlight, okay? So as I mentioned, this is very straightforward. It's like a torch, right? A flashlight, okay? So you have a range, you have an angle, and also the intensity of the light will, just drop to pitch black after a certain distance, okay? So this is spotlight. Area light, okay, so remember, this is the light that you have to bake in advance in order to show the effects, okay? So sometimes students come to me and say that I added area light, but I cannot see the effect, okay? So area light is the only light that cannot be calculated in real time in Unity by the default rendering pipeline, okay? So you have to bake it, you have to make it static, you have to make it contribute to global illumination, to the baking, and you will see the effect, okay? Okay, so yeah, speaking of global illumination, I have already introduced that, so I will not, repeat that. But in general, global illumination simply means that we consider the non-directional light or indirect light. Okay, the reflections, the lights that are bouncing off the surfaces of an object. Okay, so this kind of bouncing will also contribute to the overall rendering of your scene. Then that is global illumination. Okay. So yeah, I will just skip this. Okay, so light maps, this is also very interesting to you, right? So I guess some of you tried, if you have already tried the tutorial, I guess you may understand this. Okay, so you always do a light map baking first. Okay, so the baking process, we call it baking, but it is actually a pre-computation of how the light will be applied to an object. Okay, and then we just directly use the pre-calculated light maps to actually do another layer that is very similar to a texture. Okay, so that's the light maps, and you can always check the light maps in Unity. Okay, I have already shown that in the tutorial, so I won't cover this too much. Okay, so ambient occlusion, this is something that I haven't covered in the tutorial. Okay, because it's more like a post-processing effect. Okay, so this effect does not based on the actual model. Okay, remember, ambient occlusion happens on the screen space, not the 3D world space. Okay, not happening on the 3D world space, but the calculation may depend on some of the 3D information. Okay, may depend on some of the 3D information. So for example, this is a very typical example of ambient occlusion. So we have a point here. So in order to enhance this, the rendering of this particular point, we can apply, you can imagine we can apply a post-processing effect to this particular point. Now, how we can create such kind of effects and how this effect will look like, okay? So first of all, we need to calculate how the light, how this particular point is lighted by the entire scene. Okay, so for example, most of the light will come through this direction. Okay, so this part will contribute a lot to the the brightness of this point. Okay, so when we do the ambient occlusion, we simply want to enhance the contrast. Okay, enhance the contrast. But we only enhance the contrast where the shadow exists. Okay, so this is the objective of doing this ambient occlusion. Okay, so how will it look like? Okay, so it will look like this. Okay, so this is the original rendering. Okay, so when we add the ambient occlusion, we only enhance where shadow exists. Okay, so we enhance the so-called micro contrast in the image. Okay, the places where the shadow meets the bright part. Okay, the lighted part of your scene. So for example, this part, of course, are all the shadows, and also this part, okay, where these shadows of the top sphere will meet with these two spheres. Okay, so this is ambient occlusion. Okay, so for example, this is the calculation process, and this is basically how this point is calculated. Okay, so as you can see here, it's very similar to ray tracing actually. Okay, the calculation process, but it's a little bit easier than a ray tracing because we have already got the scene's illumination information. Okay, we do a traditional rendering first. We get the illumination information of the entire scene, and then we do this calculation. Okay, it's different from ray tracing in this sense. Okay, but the method is very similar. Okay, we shoot a ray from this point, and then we calculate the illumination within the scene. Okay, and also for ambient occlusion calculation, because the computation power needs to be very, very small. Okay, very, very limited. So it only do one-time bouncing. Okay, we shoot the ray, but we only calculate the next object it hits. We do not consider the bouncing. Okay, so this is different from ray tracing. So when I talk about ray tracing, I will explain more. So this is reflection probe. Reflection probe is another very interesting thing if you want to place some very reflective, shining surfaces in the scene. Okay, so reflection probe is also very straightforward. You just use a virtual camera. Okay, but this virtual camera is more like a 360 camera. Okay, you place it in the scene, in any point within the scene. Okay, then you can imagine this camera will take a picture of the entire scene, right, from this particular point. Okay, so then you can apply this map to the surface of those shining objects. Okay, so this is how we achieve this reflection. Okay, and also the cube map should be baked in advance. Okay, we can also do some real-time reflection nowadays, but yeah, if you have multiple reflection probes, it's better to bake it in advance. Yeah, so I guess you all know the answers. If there are moving objects, you have to use light probes instead of light maps. Okay. Yeah, so I have already expanded this. So light probes basically means that you have a lot of these data points, and each data point will be the lighting, coming to this point from the scene. Okay, and then we just do some, very interesting math behind. So for example, we know this illumination of this point A, is for example 8. Okay, and for this point B is for example 12. Okay, so if we have an object moving to this position C, okay, we can assume that between A and B, this point would be somewhere 10, and we apply 10 to the illumination of this object at point C. Okay, so that's the basic concept of light probes. And also why A point is 8, B point is 12. Well, it's based on some calculations and also pre-computations. Okay, so that's light probes. So light probes also need to be baked. Okay, in this sense. Okay, so this is the UV mapping and texturing. Okay, so I guess this is a little bit out of the scope of this lecture, but I just want to cover this a little bit. Okay, so every texture is presented as a 2D image. So you have to think a way how this 2D image can be used to wrap your object. Okay, it's just like how you wrap Christmas gifts to your friends, right? You use a 2D plane, which is a piece of paper, right? You wrap something that is in 3D, right? Normally a box. Okay, I do not have the skills to wrap some very complicated shapes, but for a box I can do it quite well. Okay, then basically you are doing the same thing for this box. Okay, yeah, so that's pretty much it for the visual rendering part, and we will move to the ray tracing part after the short break. Okay, so we will resume the lecture at 8:30. Okay, so let me resume the lecture. So we are going to talk about ray tracing and path tracing. So this is, I think this is the future of computer rendering, okay, especially given the hardware that will be available in the next few years, okay. So the biggest difference between rasterization and ray tracing or path tracing is that the beginning of the algorithm are totally different, okay. So rasterization begins at geometry or polygon level, okay? But ray tracing begins at pixel level, okay? So this is the earliest ray tracing, okay? So this analog again, okay? So how it is like so, okay? So this is actually a painter, okay, who actually invented this technique, okay? So this is the canvas he's working on, okay. So he is trying to draw this thing. I don't know what this is called. I don't know what is this. Okay, I don't know. Yeah, but anyway, you can imagine he is trying to draw this very strange object, okay. And then what he is doing is to use a string, okay. So this string, as you can see, it will pass the canvas, okay, and then reach the object, okay. So the next thing he is going to do is to directly copy the lighting here to the canvas, to the corresponding point on the canvas. Okay, so basically it's this point. Okay, so this is how he does ray tracing. Okay, so as you can imagine, this will take quite a long time to do it, right? So and also it's very easy to see to say that okay, so I just want to copy this point, right? But how you can copy it, right? How you determine the brightness of this point or even the color of this point, right? It is very difficult to do. But this is the origin of ray tracing, and it shares the great similarity to what we do nowadays in computer. Instead of using strings, we just using virtual rays, right? So they are the same. So the ultimate goal, of course, is to all ray tracing rendering methods attempt to model the same physics phenomenon, that of light scattering of various types of surfaces. Okay, so this is the ultimate goal. All ray tracing algorithms try to do the same thing. Okay, so there are lots of different ray tracing algorithms. So we of course we will not be able to go through it one by one. Okay, especially when you consider some of the real-time implementations of ray tracing, like RTX, NVIDIA RTX. That is basically a combination of the rasterization and the ray tracing. Okay, but I will try to explain the original ray tracing in its purest format, and then we can discuss how to optimize the process. The computer algorithm is always a process of optimization, right? Sometimes we propose something in the 80s, in the 70s, even in the 60s, even in the 50s, before the emergence of computer, right? And later on, we found out, okay, so the computer is not powerful enough. What we can do, we optimize it, right, to let it run on a computer at that particular era, right? So nowadays, I think we are at the era that we can replicate this rendering equation quite well. Okay, so this is the rendering equation. Basically, if you understand this equation, then you understand ray tracing in its purest format or full path tracing. Okay, so let me explain these, these different components of this formula one by one. Okay, so this one L0. Okay, so this is actually a point in the space. Okay, this is a point in the space X. And L0 is the illumination of this point in the space. You can treat it as an RGB. It doesn't matter. Okay, so you can treat it as a monochromatic kind of point. Okay, black and white from 0 to 255. Okay, or you can consider it as an RGB. It doesn't matter. Okay, so yeah, so RGB basically simply means that how this color will respond to different lights, right? Pure red light, pure green light, and also pure blue light, right? So this is RGB. So it doesn't matter. We just say this as a brightness of this point X in space. Okay. So of course this is E. E simply LE simply means this X in this how it emits light. Okay, this X, how this X emits light. Okay, so this part is how, maybe I put this. Okay, so if you decompose this part, okay, so the lighting or the brightness of this X is determined by two things. Okay, so this thing and this thing, right? So it's plus, so it's additive, right? So this part simply means that how this point will shoot light. Okay, so for example, if we want to model this one, the projector, the lens of the projector, right? So it's always giving out light. Okay, so you can imagine this part will be very large, right? So, and also you can imagine an object in the scene or in the real world must reflect some light. Okay, it is actually extremely difficult to make something purely black. Okay, so for example, my shirt, if it's purely black, you will not be able to see me. I'm basically a black hole to you. Right? So it is actually very difficult to make something purely black. Okay, so that's why you are always dealing with this part. So this is the reflection part. Okay, so now you can understand. Okay, so this point, how this point will look like to me, basically means that the light it gives out plus the light it reflects. Right? So very easy to understand. Okay, so then we can decompose. Okay, so I think for this part is very straightforward, right? It's another value from 0 to 255, right? So our focus would be this part. Okay, so this part is a little bit difficult to understand. Okay. Okay, then let's have a look. What does this part mean? Okay. So we just put this away first. Okay, so this is the integral, so I put it away. Okay, and also remember in computer we cannot actually compute integral. Okay, so this is a very important thing because this thing is continuous, but computer is discrete, right? So we cannot compute this. So it doesn't matter. We put it away first. Okay, so let me delete this part. Okay, so we will only look at this part, this part, this part. Yeah, that's it. Okay, so these three parts are very, very important. Okay, it determines, as you can see, as long as we have this, right, we have the reflection of the object or the point, right? So as you can see, these parts must determine the reflection of the point, right? Otherwise, it doesn't make sense, right? So how it's model this? Okay, so first of all, we have this Li. Okay, so this is the, as you can see here, we already marked it out. Okay, so this is the incoming light. Okay, very straightforward, right? If you want to calculate the reflection, of course, you want to understand how light shines on this particular point. Right, so this is very easy to understand, and also it shares the same format as this LIX thing, you know. Okay, so it's the same thing. It doesn't matter. The next one would be material. Okay, so this is also very important. So this is the material. Okay, so this material is a very abstract material. Okay, how can you use this omega I and omega O to actually calculate the material? Okay, so this is actually help you to calculate. If you look at carefully, you can find this one here and also this one here. Okay, so why it is like so? This function, this fx, simply tells you that how the incoming light, okay, will interact with the emitting light. Okay, so this is a super abstracted form of material. Okay, we only consider one thing. We only consider one thing. That is how light will bounce off. Okay, we only consider this thing. So of course, modern computer graphics, you know, we consider other things like the color, things like that, but it doesn't matter. Okay, it's still fx. You only plug in more parameters as the input, right? The output is still the same, either RGB or a single value from 0 to 255, right? So it doesn't matter. So yeah, when you look at you know, a lot of the formulas, if you use the computer science perspective to look at them, they are very straightforward. Okay, fx is just a function, right? You call this function, you give some input as parameters, and it returns a value. That's it, right? So yeah, so for this, it's a super simplified material representation of a material. Okay, so if you look at some of the very earliest rendering images, you will find that there is no material actually to many of you, because there is no texture. It doesn't consider texture. It does not consider, for example, bump map. Okay, so that's the material. Okay, the number is very straightforward. I guess some of you just asked this question, right? So this one, I guess I think some of you just asked this question. Okay, so this basically helps you to calculate the how the incoming light angle, okay, that can be reflected and affect the reflection process. Okay, you can imagine if you have a very, for example, you have this one. Okay, so this is the point we want to calculate, right? So of course this is normal, right? So this is the normal. Okay, so if you have a light that coming off like this, okay, you know that the bouncing off will be like this. Right, so that's it. So that's how this number thing can help you calculate. Okay, so of course, if you have this, then it will be like this. Okay, so this is a very straightforward thing. Okay, okay, so we've finished this part. We know this is the incoming light. This is how the material will react to the light, and this is a representation of how these light will be shined to the in respect to the normal of this particular point. Okay, so and also I just want to remind you one thing. Okay, so for a single point in space, you can only have, in the traditional computer graphics world, you cannot have the normal of a single point. Okay, so I think I just draw this on the whiteboard. Okay, so if you have 3 points, okay, so these 3 points A, B, and C, they are 3 vertices. Okay, and these 3 vertices will create a polygon. So this is the smallest thing you can have in computer graphics, right? So yeah, of course, you can have vertices, but vertices will not be rendered, right? You can only see these triangles. Okay, so when we determine the normal of the point, okay, we need to determine the normal of the polygon first. Okay, how we determine the polygon? It depends on how you store these 3 points. Okay, if you store them as A, B, and C, okay, if you store them like this, then basically it creates A, B, and C. It creates this direction, right? And you either use your right hand or left hand to determine the normal. Okay, how I do it? Okay, so this direction will be how my 4 fingers, okay, curved. Okay, it will be like this. So it goes into the screen. If you store it as A, B, C, okay. If you store it as C, B, A, okay, because CBA is like this, okay, so it's counterclockwise, right? So in this time, the normal will facing me, facing my direction, right? And also facing you, of course, from the screen, right? Yeah, so this is how the normal is determined. Then how we can determine the normal of these, you know, the vertices. Okay, so this is the question. Okay, how we can determine the normal of the vertices. Okay, actually, if you look at many of the shader programming, you know, programs, you will find that we don't do that. Okay, we actually don't do that. Okay, why it is like so? It's very straightforward. As I mentioned, you cannot see vertices. You can only see polygons. As long as we have the normal for the polygons, why don't we still need to calculate the normal for the vertices? We don't need, right? We don't need to do so. Okay, unless you explicitly do that. Okay, so there are still algorithms to do it. So, but I will, you know, not dive into the details. If you are really interested in shader programming, you will find a lot of materials. Okay, so if I talk about shader programming, and I think I need to have another subject to teach you how to do shader programming. Okay, so I will not. I will leave that. Okay, I will leave that to you. If you are really interested, you can find plenty of materials online. Okay, so yeah. So this back to our topic. Okay, so why we have this one? Okay, so what does this mean? Okay, what does this mean? Okay, if this is a single point. Okay, so if I tell you that this is a point on S square, now you understand it. Can you understand this? Okay, this is a point on S square. Okay, so for example, this is S square. Okay, this is the point. Then you can understand it. Okay, so if I make it more digital, more computer-like, okay, so this is not S square. This is S square. Understand it? From continuous to discrete representation. Okay, and you can see, you can imagine this must be some polygons like this, right? The topology is really poor, yeah, but it doesn't matter. Okay, so it's like this, right? So now this S square, the point on S square is like this. Okay, so the next thing we really wish to do is to calculate how the light can be shined to this point, right? So it can be like this, 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 right? So how we do that, as I mentioned, we always have one normal, so we just use the normal to calculate it, and the normal is here. Right? So this is the entire process of calculating the rendering equation. Okay, so let me put it into why I use the eraser to to erase the digital screen. Okay, so anyway, so yeah, let me just use this eraser as an example. Okay, so if we want to calculate a point, okay, so I just use one point that is very easy to calculate. Is the center of this top surface. Okay, we do not care about all the details on this surface. It's just a plain surface. Okay, so we want to calculate the point, the illumination of this point in the center of this top surface. Okay, how we do that? Okay, so first of all, we determine this, right? So is this emitting any kinds of light? Not really, right? So this is 0. Right? This is 0. Okay. So the next thing would be how we define the material. Okay. How we define the material. I just make it a little bit easier for you to calculate. Okay. So no matter how the light shines on this top surface, this point, okay, it will always reflect 20% of the incoming light. Okay, so I just give you this definition and also this, so you do no longer need to consider this, right? Because it's the reflection is very consistent. It's always 20%, right? So then this part will be 0.2, right? Then the only thing would be this one, right? Would be this one. Okay, so how we determine this one? Well, okay, I just found that maybe my calculation is too messy. I just erase this, okay, a little bit. Then how we can calculate this one? Okay, so pay attention to this and also this. Okay, so if your math is really good, you find the magic here. Okay, when you find this and this, you mean we are going to do a loop when we do the calculation, right? So this simply means that we need to see all the possible of this, right? Omega I, all the possible incoming light, and then we add them together. That's a loop, right? So in order to calculate this, we need to calculate this, right? And then when we calculate this, you find that, okay, so Li is the incoming light, but it can also be, where does this light come from? There are two possibilities. One from a light source. The second possibility is that it's from a very shiny object, a point in the scene, right? But it doesn't matter. Why it doesn't matter? If it's a very shining point, then we have this, right? And we do not have this part. For example, a light bulb. Of course, the light bulb still reflects some light, right? It's made up from glass, right? It still reflects something, but I just to give you an example, okay? In the very abstract form, a light bulb is just like this one, okay? It does not have this part, right? So we have to traverse and do this one by one for many times until what? Until we find, we do it one by one, we do it one by one, and we do it one by one, and finally we found one thing. Okay, that is the light source. We trace it back to the light source. Okay, so is that clear? Okay, let me do it again. Okay, so when you see this part and also this thing, you know that we need to calculate all the possible LIs. Right? All the possible LIs. When we calculate the LI, it is also LO, right? So then when you calculate LO, you need to calculate this LI again. So you do it once again, until you find something that does not have this part. So you no longer need to do the for loop. Right? So this part is what? This part is a light bulb. It's a light source in the scene. So remember, in the rendering equation, everything, okay, traverse back to what? Traverse back to the light source. Okay, to the light source. Okay, so that's it. So that's the rendering equation. Okay, so if you look at the rendering equation, you will find that actually when we calculate, for example, still calculate this, okay, this part. So what we need to do is like we do the emitted light first, because emitted light is 0. Okay, so I will just ignore that. Okay, so in order to calculate this LO, we have to calculate many LIs. Okay, so this is LI, maybe this is LIJ. Okay, this is LIJ plus 1. Dot until we have LIN. Right, so this is how we calculate this, right? So for this LIJ, we also need to calculate LIJK, LIJK plus 1 LIJN, right? And for this one, we also need to calculate a lot of things, right? Until what? Until we find, okay, so this one, we should stop here because maybe let me erase a little bit. Okay, so until we find that, okay, so for this one, LIJK plus 1, okay, so this is actually LE. This is a light source. Okay, so we do this through layers of layers, and until we find what? Until we find all the leaf nodes are LEs. Then we can traverse back and calculate LO. Right? So is that very clear to you? So when you look at this, when you look at this as a computer science guy or girl, okay, can you tell me what problem you are going to encounter? Just to use one word. Complex, okay? Any other answers? What? Huh? Boom? Sorry, performance. Okay, boom, okay. Okay. Yeah, so recursive, right? So for recursive things, what will happen inside the computer? We have a recursive function basically here, right? Yeah, for recursive things, why recursive algorithm will kill your computer very quickly? When you have a bug in Unity, where do you find the answer? Google it, right? And always, when you Google it, you will always find that the top answer comes from a website. Do you know that the name of that website? Stack overflow. Yes. This will quickly make Stack Overflow, right? Because it's recursive. Yeah, so that's the problem. Okay, so in many years, okay, so we have this equation long time ago, even before the computer era. Okay, we just wish to do one thing: is calculation to a non-recursive way. Okay, so that's all we wish to do. Okay, so how we can turn this into a non-recursive way and how we can optimize this. Okay, this is what we wish to discuss next. Okay, but before that, you have to really understand this. Okay, so any questions about ray tracing? Okay, so let me move on. Okay, so we have already answered that because it's a recursive algorithm, so it's very difficult to implement it in a very efficient way and very easy to have stick overflow. Okay, so this is a path tracing. Okay, so remember this is very important. Okay, so path tracing is an implementation of the rendering equation TRE. Okay, the rendering equation. So it's an implementation. Okay, even for path tracing, remember, path tracing does not equal to the rendering equation. Why it is like so? Because as I mentioned, rendering equation is something continuous. Okay, when we implement something using a computer, we are always doing some discrete approximation of something continuous, right? So this is why it is like so. Okay, and also a very important thing. Okay, so path tracing, if you look at path tracing and what I have already drawn on the screen, okay, so you will find that path tracing really saved a lot of computation power by being lazy. Okay, by being lazy. Why it is like so? Okay, so first of all, send an ray from the eye into the scene. I think everyone knows this, right? So this is also how the rendering equation tells you. If you want to calculate the point of the illumination of a point, right? You shoot a ray and do the testing. Okay. So first of all, it no longer comes from different parts in the scene, right? It starts from the pixel first, the actual pixel you can see, right? So this is the first optimization. Okay, I guess I have already talked about this. I cannot remember exactly, right? But I think maybe in lecture 1, I have already talked about that. So yeah, so the first optimization is to, instead of doing all these calculations for all the points within the scene, okay, we do it for only the points that people can see. Okay, that are the pixels. Okay, so that's why we send the ray first. So this is the first layer of optimization. Okay. Then this is very important. Send the ray from the intersection to each light. Oh, this is super smart, actually. Okay. Still remember, when we talk about the rendering equation, right? You need what to end the recursive algorithm? You need the light to end the recursive algorithm. Right? So instead of randomly searching for the light in the scenes, okay, we do one thing. We directly find the intersection to each light. Oh, this is super clever, actually. Okay, so this is the second optimization. Okay, so the third optimization is here. Spawn a new ray from reflection and refraction. Okay, so we are no longer dealing with Lij, Lij plus 1, things like that. Okay, we only do two things, two rays. One for the reflection, one for the refraction. Okay, so we only shoot two rays. Okay, so this is the third optimization. Okay,